Sulfuric acid is a highly corrosive strong mineral acid with the molecular formula H2SO4. It is a pungent ethereal, colorless to slightly yellow viscous liquid which is soluble in water at all concentrations. Sometimes, it is dyed dark brown during production to alert people to its hazards. The historical name of this acid is oil of vitriol. Sulfuric acid is a diprotic acid and shows different properties depending upon its concentration. Its corrosiveness on other materials, like metals, living tissues or even stones, can be mainly ascribed to its strong acidic nature and, if concentrated, strong dehydrating and oxidizing property. Sulfuric acid at a high concentration can cause very serious damage upon contact, as it not only causes chemical burns via hydrolysis, but also secondary thermal burns via dehydration. It burns the cornea and can lead to permanent blindness if splashed onto eyes. Accordingly, safety precautions should be strictly observed when handling it. Moreover, it is hygroscopic, readily absorbing water vapor from the air. Sulfuric acid has a wide range of applications including domestic acidic drain cleaner, electrolyte in lead-acid batteries and various cleaning agents. It is also a central substance in the chemical industry. Principal uses include mineral processing, fertilizer manufacturing, oil refining, wastewater processing, and chemical synthesis. It is widely produced with different methods, such as contact process, wet sulfuric acid process and some other methods. History. The study of vitriol began in ancient times. Sumerians had a list of types of vitriol that they classified according to the substance's color. Some of the earliest discussions on the origin and properties of vitriol is in the works of the Greek physician Dioscorides and the Roman naturalist Pliny the Elder. Galen also discussed its medical use. Metallurgical uses for vitriolic substances were recorded in the Hellenistic alchemical works of Zosimos of Panopolis, in the treatise Physicae Mystica, and the Leiden Papyrus X. Islamic alchemists Jabir ibn Hayyan, Razi, and Jamal din al-Watwat included vitriol in their mineral classification lists. Ibn Sina focused on its medical uses and different varieties of vitriol. Sulfuric acid was called oil of vitriol by medieval European alchemists because it was prepared by roasting green vitriol sulfate, in an iron retort. There are references to it in the works of Vincent of Beauvais and in the Compositum de Compositis ascribed to Saint Albertus Magnus. A passage from Pseudo-Gebera Summa Perfectionis was long considered to be the first recipe for sulfuric acid, but this was a misinterpretation. In the 17th century, the German-Dutch chemist Johann Glauber prepared sulfuric acid by burning sulfur together with saltpeter, potassium nitrate, KNO3, in the presence of steam. As saltpeter decomposes, it oxidizes the sulfur to SO3, which combines with water to produce sulfuric acid. In 1736, Joshua Ward, a London pharmacist, used this method to begin the first large-scale production of sulfuric acid. In 1746 in Birmingham, John Roebuck adapted this method to produce sulfuric acid in lead-lined chambers, which were stronger, less expensive, and could be made larger than the previously used glass containers. This process allowed the effective industrialization of sulfuric acid production. After several refinements, this method, called the lead chamber process or chamber process, remained the standard for sulfuric acid production for almost 2 centuries. Sulfuric acid created by John Roebuck's process approached a 65% concentration. Later refinements to the lead chamber process by French chemist Joseph-Louis Gay-Lussac and British chemist John Glover improved concentration to 78%. However, the manufacture of some dyes and other chemical processes require a more concentrated product. Throughout the 18th century, this could only be made by dry distilling minerals in a technique similar to the original alchemical processes. Pyrite, iron disulfide, Fe(S)(2), was heated in air to yield iron, sulfate, Fe(SO)4, which was oxidized by further heating in air to form iron, sulfate, Fe2SO4, which, when heated to 480 degrees Celsius, decomposed to iron, oxide and sulfur trioxide, which could be passed through water to yield sulfuric acid in any concentration. However, the expense of this process prevented the large-scale use of concentrated sulfuric acid. In 1831, British vinegar merchant Peregrine Phillips patented the contact process, which was a far more economical process for producing sulfur trioxide and concentrated sulfuric acid. Today, nearly all of the world's sulfuric acid is produced using this method. Physical properties, grades of sulfuric acid. Although nearly 99% sulfuric acid can be made, the subsequent loss of SO3 at the boiling point brings the concentration to 98.3% acid. The 98% grade is more stable in storage, and is the usual form of what is described as concentrated sulfuric acid. Other concentrations are used for different purposes. Some common concentrations are chamber acid and tower acid, were the two concentrations of sulfuric acid produced by the lead chamber process, chamber acid being the acid produced in lead chamber itself and tower acid being the acid recovered from the bottom of the Glover tower. They are now obsolete as commercial concentrations of sulfuric acid, although they may be prepared in the laboratory from concentrated sulfuric acid if needed. In particular, 10 sulfuric acid is prepared by slowly adding 98% sulfuric acid to an equal volume of water. With good stirring, the temperature of the mixture can rise to 80 degrees Celsius or higher. Sulfuric acid reacts with its anhydride, SO3, to form H2S2O7, called pyrosulfuric acid, fuming sulfuric acid, disulfuric acid or aluminium or, less commonly, Nonmetals acid. Concentrations of aluminium are either expressed in terms of a percent SO3 or as a percent H2SO4, the amount made if H2O were added. Common concentrations are 40% aluminium, 109% H2SO4, and 65% aluminium, 114.6% H2SO4. Pure H2S2O 7 is a solid with melting point 36 degrees Celsius. Pure sulfuric acid has a vapor pressure of less than 0.001 torr at 25 degrees Celsius and 1 torr at 145.8 degrees Celsius, and 98% sulfuric acid has a less than 1 mHg vapor pressure at 40 degrees Celsius. Pure sulfuric acid is a viscous clear liquid, like oil, and this explains the old name of the acid. Commercial sulfuric acid is sold in several different purity grades. Technical grade H2SO4 is impure and often colored, but is suitable for making fertilizer. Pure grades such as United States Pharmacopoeia grade are used for making pharmaceuticals and dyestuffs. Analytical grades are also available. There are 9 hydrates known, but 3 of them were confirmed are tetrahydrate, hexahydrate and octahydrate. Polarity and conductivity, anhydrous H2SO4 is a very polar liquid, having a dielectric constant of around 100. It has a high electrical conductivity, caused by dissociation through protonating itself, a process known as autoprotolysis. 2 hours, 2SO, 4 hours, 3SO+, 4 SO, 4. The equilibrium constant for the autoprotolysis is, Cap, 25 degrees Celsius, equals, H, 3SO+, 4, SO, 4, equals 2.7 A, 10^4. The comparable equilibrium constant for water, Kw is 10^14, a factor of 10 smaller. In spite of the viscosity of the acid, the effective conductivities of the H, 3SO+, 4 and SO, 4 ions are high due to an intramolecular proton switch mechanism, making sulfuric acid a good conductor of electricity. It is also an excellent solvent for many reactions. The equilibrium is actually more complex than shown above. 100% H2SO4 contains the following species at equilibrium: SO, 4, H, 3SO+, 4, H, 3O+, HS, 2O, 7, H, 2S, 2O, 7, H, 2O. Chemical properties: Reaction with water and dehydrating property. Because the hydration reaction of sulfuric acid is highly exothermic, dilution should always be performed by adding the acid to the water rather than the water to the acid. Because the reaction is in an equilibrium that favors the rapid protonation of water, addition of acid to the water ensures that the acid is the limiting reagent. This reaction is best thought of as the formation of hydronium ions, H2SO, 4 plus H, 2OH, 3O plus HSO4A K1 equals 2.4A, 106 A, so, 4 plus H, 2OH, 3O plus SO2A, 4A K, 2 equals 1.0A, 10 A2A, so, 4 is the bisulfate anion and SO2A, 4 is the sulfate anion. K1 and K2 are the acid dissociation constants. Because the hydration of sulfuric acid is thermodynamically favorable and the affinity of it for water is sufficiently strong, sulfuric acid is an excellent dehydrating agent. Concentrated sulfuric acid has a very powerful dehydrating property, removing water from other compounds including sugar and other carbohydrates and producing carbon, heat, steam, and a more dilute acid containing increased amounts of hydronium and bisulfate ions. In laboratory, this is often demonstrated by mixing table sugar into sulfuric acid. The sugar changes from white to dark brown and then to black as carbon is formed. A rigid column of black, porous carbon will emerge as well. The carbon will smell strongly of caramel due to the heat generated. C12H22O11 plus sulfuric acid A12C, black graphitic foam, plus 11 hours 2O plus sulfuric acid water mixture. Similarly, mixing starch into concentrated sulfuric acid will give elemental carbon and water as absorbed by the sulfuric acid. The effect of this can be seen when concentrated sulfuric acid is spilled on paper which is composed of cellulose. The cellulose reacts to give a burnt appearance, the carbon appears much as soot would in a fire. Although less dramatic, the action of the acid on cotton, even in diluted form, will destroy the fabric. C. 6 hours, 10O5, N plus sulfuric acid A6NC plus 5NH, 2O, the reaction with copper, 2, sulfate can also demonstrate the dehydration property of sulfuric acid. The blue crystal is changed into white powder as water is removed. CuSO4 of 5 hours 2O plus sulfuric acid A CuSO4 plus 5 hours 2O, acid-base properties, as an acid, sulfuric acid reacts with most bases to give the corresponding sulfate. For example, the blue copper salt copper, 2, sulfate, commonly used for electroplating and as a fungicide, is prepared by the reaction of copper, 2, oxide with sulfuric acid, CuO plus H, 2SO, 4 CuSO, 4 plus H, 2O. Sulfuric acid can also be used to displace weaker acids from their salts. Reaction with sodium acetate, for example, displaces acetic acid, CH, 3COOH, and forms sodium bisulfate, H, 2SO, 4 plus CH, 3 CuNO, 4 plus CH, 3COOH. Similarly, reacting sulfuric acid with potassium nitrate can be used to produce nitric acid and a precipitate of potassium bisulfate. When combined with nitric acid, sulfuric acid acts both as an acid and a dehydrating agent, forming the nitronium ion NO+, 2, which is important in nitration reactions involving electrophilic aromatic substitution. This type of reaction, where protonation occurs on an oxygen atom, is important in many organic chemistry reactions, such as Fischer esterification and dehydration of alcohols. When allowed to react with superacids, sulfuric acid can act as a base and be protonated, forming the H3SO4 plus ion. Salt of H3SO4 plus have been prepared using the following reaction in liquid HF, CH3, 3CO, 2SO2 plus 3HF plus SBF5A, H3SO4, plus, SBF6, A plus 23CF. The above reaction is thermodynamically favored due to the high bond enthalpy of the Cr-F bond in the side product. Protonation using simply HF-SBF5, however, have met with failure, as pure sulfuric acid undergoes self-ionization to give H3O plus ions, which prevents the conversion of H2SO4 to H3SO4 plus by the HFSBF5 system to H2SO4, H3O plus HS2O7. Reactions with metals and strong oxidizing property. Dilute sulfuric acid reacts with metals via a single displacement reaction as with other typical acids, producing hydrogen gas and salts. It attacks reactive metals such as iron, aluminium, zinc, manganese, magnesium and nickel. Fe plus H, 2SO, 4H, 2 plus FeSO, 4. However, concentrated sulfuric acid is a strong oxidizing agent and does not react with metals in the same way as other typical acids. Sulfur dioxide, water and SO42 ions are evolved instead of the hydrogen and salts. 2 hours 2SO4 plus 2ASO2 plus 2 hours 2O plus SO42. It can oxidize non-active metals such as tin and copper, depending upon the temperature. Cu plus 2 hours 2SO4 SO2 plus 2 hours 2O plus SO42 plus Cu2 plus, lead and tungsten, however, are resistant to sulfuric acid. Reactions with nonmetals. Hot concentrated sulfuric acid oxidizes nonmetals such as carbon and sulfur. C plus 2 hours 2SO4 CO2 plus 2SO2 plus 2 hours 2O, S plus 2 hours 2SO4 3SO2 plus 2 hours 2O. Reaction with sodium chloride. It reacts with sodium chloride, and gives hydrogen chloride gas and sodium bisulfate, NaCl plus H2SO4 and now HSO4 plus HCl. Electrophilic aromatic substitution. Benzene undergoes electrophilic aromatic substitution with sulfuric acid to give the corresponding sulfonic acids. Occurrence. Pure sulfuric acid is not encountered naturally on Earth in anhydrous form, due to its great affinity for water. Dilute sulfuric acid is a constituent of acid rain, which is formed by atmospheric oxidation of sulfur dioxide in the presence of water, that is, oxidation of sulfurous acid. Sulfur dioxide is the main byproduct produced when sulfur-containing fuels such as coal or oil are burned. Sulfuric acid is formed naturally by the oxidation of sulfide minerals, such as iron sulfide. The resulting water can be highly acidic and is called acid mine drainage or acid rock drainage. This acidic water is capable of dissolving metals present in sulfide ores, which results in brightly colored, toxic streams. The oxidation of pyrite by molecular oxygen produces iron, 2, or Fe2+, 2 Fe-S, 2 plus 7O, 2 plus 2 hours, 2O8 Fe2 plus 4SO2, 4 plus 4 hours plus. The Fe2+ can be further oxidized to Fe3+, 4 Fe2++ O, 2 plus 4 hours plus a 4 Fe3++ 2 hours, 2O. The Fe3+ produced can be precipitated as the hydroxide or hydrous oxide, Fe3++ 3 hours, 2O of Fe, OH, 3 plus 3 hours plus. The iron, 3, ion can also oxidize pyrite, Fe-S, 2 plus 14 Fe3 plus 8 hours, 2OA 15 Fe2 plus 2 SO2 4 plus 16 hours plus. When iron, 3, oxidation of pyrite occurs, the process can become rapid. pH values below 0 have been measured in ARD produced by this process. ARD can also produce sulfuric acid at a slower rate, so that the acid neutralizing capacity of the aquifer can neutralize the produced acid. In such cases, the total dissolved solids concentration of the water can be increased from the dissolution of minerals from the acid neutralization reaction with the minerals. Sulfuric acid is used as a defense by certain marine species, for example, the phaeophyte alga Desmarestium under-concentrates sulfuric acid in cell vacuoles. Extraterrestrial sulfuric acid, Venus. Sulfuric acid is produced in the upper atmosphere of Venus by the Sun's photochemical action on carbon dioxide, sulfur dioxide, and water vapor. Ultraviolet photons of wavelengths less than 169 nm can photodissociate carbon dioxide into carbon monoxide and atomic oxygen. Atomic oxygen is highly reactive. When it reacts with sulfur dioxide, a trace component of the Venusian atmosphere. The result is sulfur trioxide, which can combine with water vapor, another trace component of Venus's atmosphere, to yield sulfuric acid. In the upper, cooler portions of Venus's atmosphere, sulfuric acid exists as a liquid, and thick sulfuric acid clouds completely obscure the planet's surface when viewed from above. The main cloud layer extends from 45–70 km above the planet's surface, with thinner hazes extending as low as 30 km and as high as 90 km above the surface. The permanent Venusian clouds produce a concentrated acid rain, as the clouds in the atmosphere of Earth produce water rain. The atmosphere exhibits a sulfuric acid cycle. As sulfuric acid rain droplets fall down through the hotter layers of the atmosphere's temperature gradient, they are heated up and release water vapor, becoming more and more concentrated. When they reach temperatures above 300 degrees Celsius, sulfuric acid begins to decompose into sulfur trioxide and water, both in the gas phase. Sulfur trioxide is highly reactive and dissociates into sulfur dioxide and atomic oxygen, which oxidizes traces of carbon monoxide to form carbon dioxide. Sulfur dioxide and water vaporize on convection currents from the mid-level atmospheric layers to higher altitudes, where they will be transformed again into sulfuric acid, and the cycle repeats. Europa. Infrared spectra from NASA's Galileo mission show distinct absorptions on Jupiter's moon Europa that have been attributed to one or more sulfuric acid hydrates. Sulfuric acid in solution with water causes significant freezing point depression of water's melting point, down to 210 K, and this would make more likely the existence of liquid solutions beneath Europa's icy crust. The interpretation of the spectra is somewhat controversial. Some planetary scientists prefer to assign the spectral features to the sulfate ion, perhaps as part of one or more minerals on Europa's surface. Manufacture. Sulfuric acid is produced from sulfur, oxygen and water via the conventional contact process or the wet sulfuric acid process. Contact process. In the first step, sulfur is burned to produce sulfur dioxide. S plus O, 2 SO2. This is then oxidized to sulfur trioxide using oxygen in the presence of a vanadium, B, oxide catalyst. This reaction is reversible and the formation of the sulfur trioxide is exothermic. 2SO, 2 plus O, 2 SO3, in presence of E, 2O, 5, the sulfur trioxide is absorbed into 97–98% H, 2SO, 4 to form aluminium, H, 2S, 2O7, also known as fuming sulfuric acid. The aluminium is then diluted with water to form concentrated sulfuric acid. H, 2SO, 4 plus SO, 3H, 2S, 2O, 7 hours, 2S, 2O, 7 plus H, 208 2 hours, 2SO, 4. Note that directly dissolving SO3 in water is not practical due to the highly exothermic nature of the reaction between sulfur trioxide and water. The reaction forms a corrosive aerosol that is very difficult to separate, instead of a liquid. SO3 plus H, 2OH, 2SO, 4, wet sulfuric acid process. In the first step, sulfur is burned to produce sulfur dioxide, S plus O, 2, G, SO, 2, G, or, alternatively, hydrogen sulfide, H, 2S, gas is incinerated to SO, 2 gas, 2H, 2S plus 3O, 2 2 hours, 2O plus 2SO, 2, this is then oxidized to sulfur trioxide using oxygen with vanadium, B, oxide as catalyst. 2SO, 2 plus O, 2 a 2SO, 3, the sulfur trioxide is hydrated into sulfuric acid H, 2SO, 4, SO, 3 plus H, 2OH, 2SO, 4, G. The last step is the condensation of the sulfuric acid to liquid 97–98% H, 2SO, 4, H, 2SO, 4, G, H, 2SO, 4, L. Other methods. Another method is the less well-known metabisulfate method, in which metabisulfate is placed at the bottom of a beaker, and 12.6 molar concentration hydrochloric acid is added. The resulting gases bubble through nitric acid, which will release brown-red vapors. The completion of the reaction is indicated by the ceasing of the fumes. This method does not produce an inseparable mist, which is quite convenient. Sulfuric acid can be produced in the laboratory by burning sulfur in air and dissolving the gas produced in a hydrogen peroxide solution. SO2 plus H2O2 or H2SO4. Prior to 1900, most sulfuric acid was manufactured by the lead chamber process. As late as 1940, up to 50% of sulfuric acid manufactured in the United States was produced by chamber process plants. In early to mid-19th century vitriol plants existed, among other places, in Prestonpans, Scotland, Shropshire and the Lagan Valley in County Antrim, Ireland, where it was used as a bleach for linen. Early bleaching of linen was done using milk, but this was a slow process and the use of vitriol sped up the bleaching process. Uses. Sulfuric acid is a very important commodity chemical, and indeed, a nation's sulfuric acid production is a good indicator of its industrial strength. World production in 2004 was about 180 million tons, with the following geographic distribution: Asia 35%, North America 24%, Africa 11%, Western Europe 10%, Eastern Europe and Russia 10%, Australia and Oceania 7%, South America 7%. Most of this amount is consumed for fertilizers, particularly superphosphates, ammonium phosphate and ammonium sulfates. About 20% is used in chemical industry for production of detergents, synthetic resins, dyestuffs, pharmaceuticals, petroleum catalysts, insecticides and antifreeze, as well as in various processes such as oil well acidizing, aluminium reduction, paper sizing, water treatment. About 6% of uses are related to pigments and include paints, enamels, printing inks, coated fabrics and paper, and the rest is dispersed into a multitude of applications such as production of explosives, cellophane, acetate and viscose textiles, lubricants, non-ferrous metals and batteries. Industrial production of chemicals. The major use for sulfuric acid is in the wet method for the production of phosphoric acid, used for manufacture of phosphate fertilizers. In this method, phosphate rock is used, and more than 100 million tons are processed annually. This raw material is shown below as ferrapatite, though the exact composition may vary. This is treated with 93% sulfuric acid to produce calcium sulfate, hydrogen fluoride and phosphoric acid. The HF is removed as hydrofluoric acid. The overall process can be represented as Ca 5F, PO 4, 3 plus 5 hours, 2SO 4 plus 10 hours, 2OA5 Ca SO 4 2 hours, 2O plus HF plus 3 hours, 3PO 4. Ammonium sulfate, an important nitrogen fertilizer, is most commonly produced as a byproduct from coking plants supplying the iron and steel-making plants. Reacting the ammonia produced in the thermal decomposition of coal with waste sulfuric acid allows the ammonia to be crystallized out as a salt and sold into the agrochemicals industry. Another important use for sulfuric acid is for the manufacture of aluminium sulfate, also known as papermakers alum. This can react with small amounts of soap on paper pulp fibers to give gelatinous aluminium carboxylates, which help to coagulate the pulp fibers into a hard paper surface. It is also used for making aluminium hydroxide, which is used at water treatment plants to filter out impurities, as well as to improve the taste of the water. Aluminium sulfate is made by reacting bauxite with sulfuric acid, 2-AlO, OH, plus 3 hours, 2SO. 4-Al, 2, SO, 4, 3 plus 4 hours, 2O. Sulfuric acid is also important in the manufacture of dyestuff solutions. Sulfur-iodine cycle. The sulfur-iodine cycle is a series of thermochemical processes used to obtain hydrogen. It consists of 3 chemical reactions whose net reactant is water and whose net products are hydrogen and oxygen. The sulfur and iodine compounds are recovered and reused, hence the consideration of the process as a cycle. This process is endothermic and must occur at high temperatures, so energy in the form of heat has to be supplied. The sulfur-iodine cycle has been proposed as a way to supply hydrogen for a hydrogen-based economy. It does not require hydrocarbons like current methods of steam reforming. But note that all of the available energy in the hydrogen so produced is supplied by the heat used to make it. The sulfur-iodine cycle is currently being researched as a feasible method of obtaining hydrogen, but the concentrated, corrosive acid at high temperatures poses currently insurmountable safety hazards if the process were built on a large scale. Industrial cleaning agent. Sulfuric acid is used in large quantities by the iron and steel-making industry to remove oxidation, rust and scaling from roll sheet and billets prior to sale to the automobile and major appliances industry. Used acid is often recycled using a spent acid regeneration plant. These plants combust spent acid with natural gas, refinery gas, fuel oil or other fuel sources. This combustion process produces gaseous sulfur dioxide, SO2, and sulfur trioxide, SO3, which are then used to manufacture new sulfuric acid. SAR plants are common additions to metal smelting plants, oil refineries, and other industries where sulfuric acid is consumed in bulk, as operating a SAR plant is much cheaper than the recurring costs of spent acid disposal and new acid purchases. Catalyst. Sulfuric acid is used for a variety of other purposes in the chemical industry. For example, it is the usual acid catalyst for the conversion of cyclohexanoxime to caprolactam, used for making nylon. It is used for making hydrochloric acid from salt via the Mannheim process. Much H2SO4 is used in petroleum refining, for example as a catalyst for the reaction of isobutane with isobutylene to give isooctane, a compound that raises the octane rating of gasoline. Electrolyte. Sulfuric acid acts as the electrolyte in lead-acid batteries, at anode, Pb plus SO, 42AAA Pb SO, 4 plus 2A, at cathode, PbO, 2 plus 4 hours plus SO, 42A plus 2ALA Pb SO, 4 plus 2 hours 2O. Overall, Pb plus PbO, 2 plus 4 hours plus 2SO, 42AAA 2 Pb SO, 4 plus 2 hours 2O. Domestic uses. Concentrated sulfuric acid is frequently the major ingredient in acidic drain cleaners which are used to remove grease, hair, tissue paper, etc. Similar to their alkaline versions, such drain openers can dissolve fats and proteins via hydrolysis. Moreover, as concentrated sulfuric acid has a strong dehydrating property, it can remove tissue paper via dehydrating process as well. Since the acid may react with water vigorously, such acidic drain openers should be added slowly into the pipe to be cleaned. Health. Sulfuric acid and sulfonated phenolics are the primary ingredients in Debacterol, a liquid topical agent that is used in the treatment of recurrent aphthous stomatitis or for any procedures in the oral cavity which require controlled, focal debridement of necrotic tissues. Safety. Laboratory hazards. Sulfuric acid is capable of causing very severe burns, especially when it is at high concentrations. In common with other corrosive strong acids and strong alkalis, it readily decomposes proteins and lipids through amide hydrolysis and ester hydrolysis upon contact with living tissues. In addition, it exhibits a strong dehydrating property on carbohydrates, liberating extra heat and causing secondary thermal burns. The strong oxidizing property may also extend its corrosiveness on the tissue. Because of such reasons, damage posed by sulfuric acid is potentially more severe than that caused by other comparable strong acids, such as hydrochloric acid and nitric acid. Accordingly, it rapidly attacks the cornea and can induce permanent blindness if splashed onto eyes. If ingested, it damages internal organs irreversibly and may even be fatal. Protective equipment should always be used when handling this acid. Moreover, its strong oxidizing property makes it highly corrosive to many metals. Sulfuric acid must be stored carefully in containers made of known reactive material. Solutions equal to or stronger than 1.5 am are labeled corrosive, while solutions greater than 0.5 am but less than 1.5 am are labeled irritant. However, even the normal laboratory dilute grade will char paper by dehydration if left in contact for a sufficient time. The standard first aid treatment for acid spills on the skin is, as for other corrosive agents, irrigation with large quantities of water. Washing is continued for at least 10 to 15 minutes to cool the tissue surrounding the acid burn and to prevent secondary damage. Contaminated clothing is removed immediately and the underlying skin washed thoroughly. Preparation of the diluted acid can also be dangerous due to the heat released in the dilution process. The concentrated acid is always added to water and not the other way around, to take advantage of the relatively high heat capacity of water. Addition of water to concentrated sulfuric acid leads to the dispersal of a sulfuric acid aerosol or worse, an explosion. Preparation of solutions greater than 6 m in concentration is most dangerous, as the heat produced may be sufficient to boil the diluted acid. Efficient mechanical stirring and external cooling are essential. On a laboratory scale, sulfuric acid can be diluted by pouring concentrated acid onto crushed ice made from deionized water. The ice melts in an endothermic process while dissolving the acid. The amount of heat needed to melt the ice in this process is greater than the amount of heat evolved by dissolving the acid, so the solution remains cold. After all the ice has melted, further dilution can take place using water. Industrial hazards. Although sulfuric acid is non-flammable, contact with metals in the event of a spillage can lead to the liberation of hydrogen gas. The dispersal of acid aerosols and gaseous sulfur dioxide is an additional hazard of fires involving sulfuric acid. The main occupational risks posed by this acid are skin contact leading to burns and the inhalation of aerosols. Exposure to aerosols at high concentrations leads to immediate and severe irritation of the eyes, respiratory tract and mucous membranes. This ceases rapidly after exposure, although there is a risk of subsequent pulmonary edema if tissue damage has been more severe. At lower concentrations, the most commonly reported symptom of chronic exposure to sulfuric acid aerosols is erosion of the teeth, found in virtually all studies. Indications of possible chronic damage to the respiratory tract are inconclusive as of 1997. In the United States, the permissible exposure limit for sulfuric acid is fixed at 1 mg per meter 3, limits in other countries are similar. There have been reports of sulfuric acid ingestion leading to vitamin B12 deficiency with subacute combined degeneration. The spinal cord is most often affected in such cases, but the optic nerves may show demyelination, loss of axons and gliosis. Legal restrictions. International commerce of sulfuric acid is controlled under the United Nations Convention Against Illicit Traffic in Narcotic Drugs and Psychotropic Substances, 1988, which lists sulfuric acid under Table 2 of the Convention as a chemical frequently used in the illicit manufacture of narcotic drugs or psychotropic substances. In the U.S., sulfuric acid is included in List 2 of the list of essential or precursor chemicals established pursuant to the Chemical Diversion and Trafficking Act. Accordingly, transactions of sulfuric acid are such as sales, transfers, exports from and imports to the United States are subject to regulation and monitoring by the Drug Enforcement Administration. See also, Aqua Regia, John George Hay, Katie Piper, Piranha solution, saving face, sulfuric acid poisoning, sulfur oxide. References. External links, International Chemical Safety Card 0362, sulfuric acid at the periodic table of videos, NIOSH Pocket Guide to Chemical Hazards, CDC sulfuric acid NIOSH Workplace Safety and Health Topic, External Material Safety Data Sheet, Calculators, Surface Tensions, and Densities, Molarities and Molalities of aqueous sulfuric acid analysis titration freeware, process flowsheet of sulfuric acid manufacturing by lead chamber process.